Hi guys, Dr. Kruse here, elementary statistics. We're going to do quite a bit today. We're going to determine probability that something happens, probability of an event, and we'll determine the probability of its complement. It either will happen or it won't happen. We'll talk about the law of large numbers. We're going to compare relative frequency versus theoretical probability, and I'm going to try to explain sample space. All right, first thing I want to do is just a quick review of rounding. So I just made up this number, 3.45621, and I just want to review rounding to 1, 2, 3, or 4 decimal places because in statistics, we're going to round to 4 decimal places a lot. So let's just review that real quick. If I say 1 decimal place, that means I need one number after the decimal. See if I can point to it here. All right, so I'm going to keep the 4, the first number after the decimal. That's 1 decimal place. So 3.4 is my answer unless we take a peek at that next number and it's 5 or bigger. If that next number is 5 or bigger, then I have to round that 4 up to a 5. So 3.5 to 1 decimal place. All right, 2 decimal places. Keep 2 numbers after the decimal. So my answer looks like 3.45, but before you write it down, take a peek at the next number. All right, 2 numbers, set 2 decimal places. Take a peek at the next number. If it's 5 or bigger, you got to round that up to 6. So 3.46. Let's go 3 decimal places. So there's 4, 5, 6. Those are my 3 numbers after the decimal, my 3 decimal places. Before you write down 3.456, take a peek at the next number. And if it's 5 or bigger, you got to round up. It's not. So we leave that one, 3.456. And finally, 4 decimal places. There's 4 numbers after the decimal. Before I write it down, I want to take a peek at the next number, and if it's 5 or bigger, I'm going to round that 2 up. 1 is not, so I leave it 3.4562. All right, just a little quick review of rounding there. Next, I want to talk about the weather. All right, if you watch the weather on TV, they'll say the probability of rain. We use capital P, uppercase P for probability. Probability it's going to rain, maybe they said it was 70%. Which means 0.70. If you're speaking percent, it looks like this, and if you're speaking decimal, it looks like this, but they're the same thing. So maybe the weatherman or weatherwoman says probability of rain today is 70%. Well, that means the probability that it's not going to rain is 30% or 0.3. If we add the percents, they add up to 100%, and if we add the decimals, they add up to 1. So your probabilities always have to add up to 1. All right, they always have to add up to 100%. But we usually write probabilities in decimal form, so your probabilities always have to add up to 1. If we're simply talking about an event, we call this an event, whatever we're measuring, and its complement. If you're just talking about those 2 probabilities, just make sure they add up to 1. Over here is just a quick way of finding that 30. If you know the probability is 70%, well, to find the 30, easy way is just take the 70 away from the 100 to get your 30. So to find that 30%, just take 1 minus that probability. All right, we kind of did that in our head, but when the numbers get trickier and you want to find the complement, just take the probability away from 100, away from 1, and that'll give you the probability of the complement. So this is the event, and this is the complement of the event. It either does or it doesn't. It is or it is not. All right, here's some notation. So we could say probability of rain. We could abbreviate rain to R. Probability of R. All right, that's our event. This isn't real common, but this is the probability of not rain. It's the probability of the complement of the event. The event was rain. The complement is not rain. All right, so this is the complement of rain. This is the probability of the complement of rain. It's basically just the probability that it won't rain. Okay, next, if rain's certain, if we are 100% sure, then our probability is 1. All right, if the probability of rain is 100%, well, 100% when you speak decimal is 1. See up here, 100% is the same as 1. So if you're sure of something, then your probability is 1. If it's impossible, if there's no chance of rain, then the chance is 0. All your probabilities are going to lie between 0 and 1. Next thing we'll talk about is relative frequency. All right, that's calculated by just taking the number of occurrences divided by the number of total outcomes. All right, or the number of values in your table. So if you got a big table with a bunch of values in it, the number of times something happened divided by the number of values in your table, all right, versus what's called theoretical probability. I like to think of it as the sample versus the population. All right, relative frequency comes out of your values in your table, and your table is just a set of measurements that you made off of your sample. All right, so relative frequency, how often something occurs out of your table of values, your sample. Theoretical probability is what is supposed to happen in the population. Lots of times I'll explain this as maybe the weight of the average weight of fish in a lake. All right, now theoretically, in theory, I could calculate that. All right, I could have a big net manufactured and I could drop it to the bottom of the lake and I could have a bunch of helicopters lift that net up and I'd grab all the fish and I'd have scales hooked onto the helicopters so we could weigh the fish, and then we'd drop them back down into the lake. And I would have all of the fish's weights. I would add them up and divide by how many fish there were. All right, but nobody's going to do that. Nobody's going to make that big net. Nobody's going to rent all those helicopters. So in theory, it could be done. Theoretically, it could be done. All right, but nobody's ever going to do it. This is going to be something that we guess at. Your population number is something that we have to estimate or guess at based on the ones that we could catch. Your sample is kind of the fish that you could catch. Maybe I can go out and catch 30 fish or 100 fish or 1,000 fish. All right, maybe I caught a big sample. Maybe I caught 1,000 fish and I said, I weighed all the fish, I add them up and divided by 1,000, and I said my average, my X bar, my sample average, my sample mean is 3.5 pounds. Well, that's an estimate of the average weight of a fish in the lake. All right, that's an estimate of the population. This number that we'll never really know, because we'll never be able to gather up all the fish in the lake and weigh them and add up that weight and divide by how many there are. We'll never be able to do that, but we can make an estimate of it with our sample. All right, so relative frequency is an estimate of theoretical probability. Theoretical probability is kind of mathematically what it should be, even though we won't be able to calculate it. What we do instead is we take a sample and we make an estimate of what, in theory, that number should be. It's kind of an educated guess. Which brings us to the law of large numbers. I call this the Vegas law. All right, this is how Las Vegas stays in business. All right, they have all games, all casino games, calculated so that the probability is slightly in Las Vegas's favor. For example, blackjack. If you play blackjack and you're really good, you have a 49% chance of winning. But that means that means Las Vegas has a 51% chance of winning. Now you might go in there one time and win, all right, and you feel like a winner because you played blackjack and you beat Vegas. But if you go back again and again and again, if you go back 10 times, 100 times, 1,000 times, 10,000 times, eventually, if you go back long enough, the law of large numbers takes over and the win-loss percentage becomes what it should be, where you win 49% of the time and Vegas wins 51% of the time. So the more you go back, the larger those numbers get, the more it falls in line with, in theory, what it should be. Theoretically, you should only win 49% of the time. And that happens when you go back a large number of times. So as your sample size gets bigger, as you go back to Vegas over and over and over again, eventually the numbers fall in line to what the theoretical probability states they should be. So relative frequency will get closer and closer to theoretical probability as the sample size gets bigger, as you keep going back to Vegas over and over and over again. All right, your sample calculations get closer to that actual number that we'll never be able to calculate. That's actually just a theory. It's theoretical. Your predictions get closer to your theory. Your X bar gets closer to mu. All right, as your sample size gets bigger. Lots of times we say, oh, a sample size of 30 is pretty good. All right, we can use 30 values and make a pretty good prediction about the actual number, the theoretical probability, the population mean. All right, But the bigger your sample size gets, the better your data is going to be, the closer you will be to the actual population number. All right, that's the law of large numbers. The more values you collect, the bigger your sample is, the closer your data gets to that theoretical probability, that actual number, that population mean. All right, here's a simple little table just to practice calculating some simple probabilities. So maybe a good study skills contain four things, all right, are comprised of four things. Students who arrive early, they take good notes, they complete their homework early, and they seek help when needed. Maybe that's four good study skills. And maybe I go out and I survey 375 students, and I ask each one, I say, hey, how many of these do you do? How many of these good study skills do you do? Well, some people will be very good students and they'll do all four study skills. In this case, we said that 33 students out of the 375, 33 out of 375 did all four study skills. And 125 students reported that they did, well, we did 3 out of the 4. And 119 students reported, well, we do 2 of them. 70 students reported that they did only 1 of these 4 study skills. And don't forget about 0, all right? There are going to be some students who do none of the study skills for a total of 375 students. So even though I have 4 options here, all right, there's actually 5 different possible outcomes. They could do 1 of them, they could do 2, they could do 3, they could do all 4, but they could also do none. This is what's called the sample space. All of the possible things that could happen, all of the possible outcomes. They could possess all 4 study skills, 3, 2, 1. Lots of people forget about 0. There's some people who don't do any of those. All right, so let's calculate some relative frequencies is all we're doing. And what's the probability that I grab a student at random? What's the probability that that random student does 0 of the study skills? Well, there were 28 out of 375 that said they did 0 study skills. That's about 7% when we round this to 2 decimal places. What's the probability that a randomly selected student only does 1 of the study skills? Well, 70 out of 375 said they only did 1. That's about 19%. So the probability of randomly selecting a student and they only do 1 of the study skills is 19%. 19 out of 100 times you're going to randomly select a student who only does 1 of the study skills. And we can go on down the line here. What's the probability that you select a random student, you just draw a student's name out of a hat, and they only possess 2 of those good study skills? Well, 119 out of 375 reported that. There's a 32% chance that you draw a person out of a hat, randomly selected, and they only possess 2 of those study skills. What's the probability that a student randomly selected possesses 3 of those study skills? About 33%. So out of every 100 times you go into the hat, 33 of those draws will be people who possess 3 of those study skills. What about all 4? Well, that's not very many. 33 out of 375 reported all 4 study skills. That's about 9%. So if you draw out of the hat, randomly selecting students' names out of a hat 100 times, 9 of those times you'll pull out a student who possesses all 4. Remember what these guys got to add up to. 7%, 19%, 32%, 33%, 9%. That adds up to 100%. But we're speaking decimal here, so it adds up to 1 when you're speaking decimal. Okay, what about multiple probabilities? For example, somebody could ask you, well, what's the probability I reach into the hat, or I reach out in the hall and I grab a student, and that student has at least 1 of those study skills, those good study habits. So what's the probability I reach out into the hall, I randomly grab a student, and they possess at least 1 of those study skills? Well, think about what at least 1 means. At least 1 means you could have 1, or you could have 2 of the study skills, or 3 or 4, all right? I could have any of those. So I could grab a student who has 1 of the study skills. I could grab a student who has 2. I could grab a student who has 3 of the study skills. I could grab a student who has 4. The chance of each one of those is written here, which adds up to 93%. So there's a really, really good chance that I reach out into the hall, randomly grab a student, and that student has at least one of those study skills. We just simply add up the individual probabilities. Another way of writing it is probability that the student I grab, X, has more than or equal to 1. That says the same thing here. So the student can have one of the study skills, but they can also have more than one of the study skills. They can have one, or they can have more than one. All right. A quicker way to do this, if you like shortcuts, is if you're looking for everything but 0, which is what we're doing. We said it can have 1, 2, 3, 4. They can have all of these except the probability of 0. Well, a quick way to do that is just take the 1, the 100%, and take away the one you're not talking about, 7%, to get a 93%. We wind up at the same place. It's just a short way of doing it. So instead of adding up a whole bunch of individual probabilities, why don't you just start at 100% and take away the one probability you weren't talking about? Okay, now we got to be careful here. The probability of less than 2 and the probability of less than or equal to 2, we got to differentiate between those two. Probability that I grab a random student out of the hallway and they have less than 2 of the study skills. Well, what does that mean? If mom says you can have less than 2 pieces of candy, that means you can't have 2. You can have 1 or you can have none. So I can't have 2. I can have less than 2. That means I can have 1 or I can have 0. So that student out in the hall that I grabbed, randomly selected, could either have none of the study habits or 1 of the study habits. So that's probability of 0 plus probability of 1. That's about 26%. Another way of saying less than 2 is just using the less than symbol. So the probability that the student I selected at random has less than 2 of the study skills is the probability of no study skills plus the probability of 1 study skill, versus less than or equal to 2. All right. You could also say X is less than or equal to 2. You could also say no more than 2. These all mean the same thing. So if mom says, hey, you can have no more than 2 pieces of candy, that means you can have 2. Or you could have 1 or you could have none. All right? No more than 2 means 2 is okay. So I can have 2, but no more than 2. I can't have 3. I can't have 4. I can have no more than 2. So I can have 2 and 1 and 0. So probability of 0, probability of 1, probability of 2. It's about a 58% chance. So what are the odds? What's the probability that I reach out into the hall, grab a randomly selected student, and that student has less than or equal to 2 study skills? Well, that means they could have 2 study skills, but they could have less. They could have 1 or they could have none. Add those up, there's a 58% chance that they have no more than 2 of the study skills. All right, and then one last thing here, probability no more than 3. Another way they might say that is 3 or less, or X is less than or equal to 3. These all mean the same thing. If mom says you can have no more than 3 candies, that means you can have 3, but no more. You can't have 4. You can have 2, you can have 1, you can have 0, but no more than 3. Add those up. You have a 91% chance of reaching out into the hallway and randomly selecting a student who has no more than 3 of those study skills. That's a really good chance, 91% probability. All right, if there's a 91% chance it's going to rain, that's a really good chance that it's going to rain. So this is a really good chance that you can randomly select a student that has no more than 3 of those study skills, or 3 or less of those study skills. Okay, and the last thing I want to cover is I want to introduce you to some given that situations. So given that something happened first, what's the probability of the second thing happening? So maybe you're standing outside a store, you're one of those clipboard people, you're taking a survey and you're measuring how many people walk by, all right? So you're standing outside a store and you notice that you mark on your clipboard that 137 people walk by, and then you notice that 54 of these actually went in the store. The rest of them just kept on walking on by. And then somebody inside the store said, well, out of those 54 that came in, hey, 21 of them bought something. All right, this is all valuable information for a storekeeper. If they know how many people are in town, they can kind of predict how many people are going to buy something from their store. So I just did the same thing here with the tree diagram. I said, okay, 137 walked by. They told us that. Now, they either came in or they did not come in. This is the event. This is the complement of the event. So if they told us 54 came in, then we can do a little subtraction and figure out that 83 did not come in. That's the complement of the event. If they tell us that 21 bought something, then we can do a little subtraction and find out that 33 did not buy something. This is the event. This is the complement of the event. All right. And the only reason I do that is sometimes they ask you about probabilities involving the numbers that they did not give you. All right. So what's the probability? Let's start right here. What's the probability a person who walks by will enter? All right. So we got to kind of think about what happens first and what happens second. First, they walk by, and then second, they turn and enter the store. All right. How many people walked by? 137. That was given. How many people entered the store? 54 came in. 54 entered the store. So 54 out of 137. All right. Out of 137 people that walk by, that's the walk by number, 54 came in the store, about 39%. Now there's lots of ways to set up this fraction. Most people just put the larger number on bottom. All right. That kind of makes sense because you want your fraction to turn into a number between 0 and 1. And for that to happen, the number on top needs to be smaller. All right, so if this confuses you, you're pretty safe just putting the larger number on the bottom. All right, the first event goes on the bottom, if you want to think about that way. If we want to go a little bit deeper, whatever happened first, all right, did they walk by first or did they enter the store first? Well, first they have to walk by, and then they decide to enter the store. This is the first event, and the first event goes on bottom. The second thing that happened goes on top. So given that they walked by, all right, that has to happen first. Given that they walked by, how many went in? So 54 out of 137. All right, these are the same numbers here. I'm just showing you some notation. So this says probability a person who walks by will enter. This is notation. That's the probability that they enter given that they walked by. All right, this is the first event. This is the second event. I know it seems kind of backwards. We're listing the second event first, but that's the way we list this thing. We say probability that they enter given that they walked by. This is the first thing they did. This is the second thing they did. Given that is going to turn into a fraction bar right here. Now, if we write it left to right horizontally like this, our fraction bar stands up vertically like this. That's just the fraction bar there. So to shorten this a little bit, we just change the words given that to a vertical fraction bar. The probability that they enter given that they walked by. This is the first thing they did. This is the second thing they did. This is an even shorter version. The probability that they enter given that they walked by. This is the first thing they did. This is the second thing they did. All right. So the first thing they did was walk by. So out of the people that walked by, 137, how many entered? 54. All you're doing is just kind of standing this fraction up. You're just kind of turning it and putting the E on top and the W on bottom, and that turns into a fraction bar. You're just kind of spinning it to the right clockwise to get your 39%. Okay, so let's do it in English first, and then we'll kind of write it statistically. So what's the probability a person who walks in will buy something? Well, what happened first? First, they had to walk in the store, and then they bought something. This is the first event. This is the second event. 54 people walked in, 21 bought something. So let's write it a little more formally. The probability that they'll buy, given that they walked in. They had to walk in first, and then they bought something. This is the first event. This is the second event. So 21 bought out of 54 that walked in. Out of 54 that walked in, 21 bought something. So 39% of the people who walk in the store will buy something. That means 39 out of 100. That means out of every 100 people that walk in the store, 39 will buy something. That's the kind of information a store can use. All right, what about the probability a person who walks by will come in and buy something? That's getting kind of complex here, but let's just make a simple fraction here. What did they do first? Well, first they had to walk by. That's going to be my bottom number, what they did first. What'd they do after that? Well, they came in and bought something. So if we go back to our tree diagram, we know that 54 came in. How many bought something? 21 ended up buying something. So the probability that someone will come in and buy something, given that they first walked by, all right, how many walked by? 137. How many ended up buying something? 21. So there's only a 15% chance that a person walking by on the sidewalk will actually come in and buy something, all right? If they walk in the store, there's a 39% chance they'll buy something. But if they're just walking by on the sidewalk, there's only a 15% chance that they'll come in and buy something. Now, let's do one more here. What's the probability somebody buys nothing, given that they came in the store? So first they came in the store, but they ended up buying nothing. Well, we had to do a little subtraction to find that number. How many people came in the store? 54. How many bought nothing? Well, we know that 21 bought something. And doing a little subtraction means that 33 bought nothing. We did that up above. So given that they first came in the store, that's 54 people came in the store, how many of those 54 bought nothing? 33 bought nothing. 33 out of 54, that's 61%. So of the people who come in the store, 61% won't buy anything, all right? That's 61 out of 100. Out of every 100 people that come in the store, 61 will not buy something. All right, that's all I got for today.